party from Korea, from Pahang, Institute of Basic Science, new institute. And Jehun will talk about, I think, our joint result, which we did in Vienna in August.
All right, thank you for the introduction. And I will talk about the 28 nodal Pezzo threefold of degree 1 and the smooth plane quadratic curve. So here my Pezzo threefold. As a final threefold with Greenstein terminal singularities. Such that this anti-canonical divisor is divisible by 2. And then the cubed h will be called the degree of this Pezzo threefold. So this is the degree of the x. And it's known that this degree and the length of this class group is at most 9. And it's known that the h is the Cartier. So and that this number is d is between the 1 and 8. Okay? So here in my talk we are interested in this Pezzo threefold with the maximal number of the singularities, in particular degree 1 case. So here is the table for the maximal number of the singularities, and this is due to the Prokhorov. So here's the degree, and here's the number of the maximal number of singularities: 6, 5, and here is 4, 3, 2, 1, and here 6 is 1, and this is 3 and 6 and 10 and then 16, and then this is 28. Right? And also Yura proved this type of the Pezzo threefold can be given by anti-canonical model. Models of the blow-ups P3 at the A minus D points with the certain conditions. So let me give you details about this construction. So let me explain this condition. So this condition means if there is at least 2, then this condition means 8 minus D points. So in linear general position. Meaning that there are no 4 points of them lie on a plane. Okay, this is the condition for the case degree at least 2. And when the degree is 1, so we have the extra condition. So first 7 points, again, a linear general position. Okay, this is the first. And second, no twist cubic curve. cubic curve pass through this 7 point, the 7 points. Okay. And we have one more extra condition for this. Let me describe this condition by picture. So, all right. So you have, if you have the 6 point this way, 6 point out of this 7 point, then you have this twist cubic which pass through this 6 point. Right? The 6 points in general position, linear general position, determines the one twist cubic. Right? Then you have the one more point outside. All right, and then let's say this is the PI and this is the PJ, and then you choose the line which determined by these 2 points. All right, let's say this is a C and this is R, and C intersection R, this intersect transversally, and this is the only, this PI is the only intersection point. So that's the condition. This 7 point must satisfy this condition. Okay. All right. So this is the condition which satisfy. I mean, which must satisfy. All right. So I will denote this condition by asteroid. Okay. I will explain this condition in detail later. All right, so let me go on. There's a Prokop's construction for the degree 1 case. No. Oh, this is the Delphi surface case with the maximal number of singularity. So if degree is n is 3, then here you see you have this much point, which is the a minus b point, right, to blow up. So this number is the n minus 5. So you have this is this a minus d points is the unique of the project transformation in P3, right? So this is the unique up to P0. Right. So up to here, this Delphi is the unique. Right. So for example, like this cubic case, this is a famous the circular cubic. Circular cubic, which has the 10 nodes, right? Which is defined this way. So this is let me define this way. X5 Q0 and X0 X5, this is 0, and this is in P5. Okay. All right, and the degree 2 case. All right, this case is unique, as I explained before. All right, here you have what? You have a one point freedom. So in P3, so it's a 3-dimensional family, right? So actually, this is the double cover. P3, the ramifies along, branched along. Kumho quartics. All right, so Kumho quartic has the 16 nodes exactly. So and this guy also. So this double cover also has the 16 nodes. So this is the 3-dimensional family. All right, the same as the dimension of the family of genus 2, right? All right.
These are maximum number of singularities.
Yeah, it's a maximal number of singularities.
Then there must be some force in the 3-dimensional.
What do you mean?
Well, if there is a family.
But the number is the fixed. But you have to reduce I mean, otherwise, I mean, if then the number of the singularities, not the 16.
Usually, when there is a family, then some special elements are more singular.
But they don't isolate it.
That's what happens.
But it's a Q-Greenstein. I mean, the Greenstein and terminal singularities.
All have the same number.
All right, and now let me explain the degree 1 case. So 28 the singular points. Okay. So we have 7 points in P3. All right. All right, then you have 21 lines determined by the 2 point out of the 7, right? So this is the 7. I mean 2 choose 7, right? 2 choose 2. I mean 7 choose 2, right? In lines, Lij, let's say determined by Pi, Pj out of this 7 point, right? And you have 7 twist cubic, cubics, determined by 6 point out of this 7 points, by 6 points out of this 7 points, right? Okay, let me erase this. All right, and now we take the blow of along this 7 points. So let me denote by tilde. All right, so you have this 21 lines and the 7 twist cubics. Let's say Ci, okay. Ci, and then you consider this proper transform. All right, and if you look at this condition, then you can easily check this 28 curves disjoint each other. Okay? They are separated. All right, and let's see the this canonical divisor. I mean anti-canonical divisor. This is the fallback of this minus KP3 minus, let's say, this is exceptional divisors, right? Right, and you take the intersection, then you can, I mean the intersection on this guy, you can easily see it's a trivial, and also this guy is a trivial, right? And the normal bundles. So if you take the blow up from the curve, then you got the 1 minus, right? Then you got minus by 1 each time. So the normal bundle of the line is the O1 plus O1. So you take the 2 blocks. That means the upstairs is this. And I think this twist cubic is O of 5 plus O of 5. So you take your 6 blocks, right? So you get the same. So that means you can contract this curves. I mean, by plopping contraction, you get your node, right? So you have this let's say this is a V. This is mu, and this is a propping construction. Algebra. Yeah, anticanonical, yeah. So you get this. You have 28 different curves which contract to the 28 nodes, right? So that's why I mean this is the way to construct the. I don't know. We have to check. So
you're plotting both the CI and the lambda.
yeah, you plot. I mean you contract this 28 curves. Then you get each. So first of this by this. So you get CI, and the image will be a node, and the number of nodes is exactly 28, right? Okay, this. And then you see this is the only. I mean, this is the only curves which intersect the minus k trivially, and the other curves intersect positively. And so, like this, V is ample, and of course this is divisible by divisible by 2. So this H is comes from the quadratic surface which pass through this 7 points in P3, right? And this number, the cube is exactly this minus P3, and see this is exactly 1, right? So this is the reflection of 3/4 of degree 1 with exactly 28 singular points. Right? All right. So this is the Prokhorov's construction. So, all right. So let me explain the new approach to this construction. All right, so I want to look at this condition with a different point of view. All right, so for this we consider a linear system of the quadratics. This is the linear system. Quadratics. MP3 passing through this 7 points. Right. All right. So and we can check this condition is equivalent to the following. So first, this is equivalent to first. The base locus of this linear system must consist of the 8 different points, 7, so P1 up to P7, and then we have extra base point. And second condition is every member must be irreducible. So every member and here is irreducible. So these two conditions are equivalent to this stuff. This proof is I mean, it's elementary. So like you don't need big tools for this, but it's quite it takes a time, but yeah, it's not hard. So this reinterpretation of this condition, it connects to the classical theory about the Cayley octets. So if A points satisfy this condition. I mean, A point comes from the net of quadrics, the base locus of the net of quadrics. Then it's called the Cayley octet. This is called the Cayley octet. This A points is called the Cayley octet. Okay, and also if Cayley octet, I mean satisfy this condition, meaning the linear system, I mean the net of the quadric, which defines this Cayley octet, satisfy this condition, then we say this Cayley octet is regular. So regular Cayley octet. All right. So this is very classical things. All right. And then let me explain why people call this octet is, if satisfy this condition, then this Cayley octet is called the regular. All right, so here our linear system, dimension of this linear system is, as I said, is the two-dimensional. It's a net of quadrics. All right, then this is generated by, so let's say, let's use this x, f1, plus x, y, f2, z, f3. So this is the f1, f2, f3 is the equation of the quadrics, and the x, y, z. All right, so this is the parameter from here. All right. But here you may consider this guy as the 4x4 symmetric matrix, right? Linear 4x4 symmetric matrix. So you take the determinant of this guy. Now, or you will have the you take the determinant, and then you consider the curve which defined by plane curve defined by this determinant. All right, that will be a quartic. Right. So let's denote here this curve, C in P2, and this is a quartic. Right. And in classical terminology, this quartic is called the Hessian of this net. So this is called the Hessian. Hessian of the net of L. Right. Right. Now I can erase this. And so I'm not going to prove this, but with some elementary argument, you can prove this condition is equivalent to the condition that this Hessian curve is smooth. So that's why people call this kind of the Cayley octet is regular. So this is the equivalent condition. Okay. All right. So this is the classical interpretation of the original condition stuff. All right. So let me get back to the derivative report of degree 1. Okay. So here. So, all right, this is our derivative report. Degree 1 with the Gorenstein terminal singularity. Right, then you can embed in the this P1, 1, 1, 2, 3 by hypersurface of degree 6. Right? All right, so let me use this variable ST U V W. Then you can say this guy defined by this equation. 3. So let me use this. STU, V, and G6, STU. So this is the homogeneous equation of the, homogeneous polynomial of degree 4 in STU and degree 6. Okay. All right, this is the standard form. All right, and so this half anti-canonical linear system has the base locus, so exactly here, STU0 and this notation. This is the extra. This point comes from the extra base locus. The base point of the net. All right. Okay. Where is this? All right, and then you see this is P2. All right, so we have this elliptic vibration structure. So blow up, you take the blow up, P. Okay, so this is VR, and this is our elliptic vibration. Right, and this is our plucked-in contraction, and this is our blow up, P3. And this map given by this our linear system L, right? Okay. All right. So here we have the elliptic vibration, and the general fiber comes from the intersection of the two quadratics of the in the net L, right? So general fibers, and our discriminant locus is given by this equation, just standard things. Right, starting from here, this equation, this is the bias transform of the elliptic curve over the function field, STU. So will be given by this, right? All right, so you have. And then we want to look at this J invariant function. So each point here, STU. So in general case, you're gonna have the elliptic fiber. The elliptic curve, and then we assign the J invariant. So we have the J invariant. Actually, this is a rational function. This guy. It's elliptic vibration, P2. This is given by this, J S T U. So this is also 1728 divided by, you have 4 times the cubed, and this is a discriminant, right? All right, so this is our J function, all right? All right, and this is from the net, but I want to reconstruct our this Delphi default from the quartic, the Hessian quartic. So let me erase this. All right, so for a while we forget everything, and then we just consider this curve, a smooth, and this is a smooth plane quadratic, plane quadratic. Let's say defined by f. F, let's say x, y, okay. And we consider dual point as t, u, and here p2 dual. Okay. All right, so then this is a dual plane. All right, this guy will define the line on the p2. So let's say s, x, t, y plus u is equal to 0. Okay. All right. Then let's say this line is L, and suppose this guy is general. Then this. So you have quadratic, and then smooth. Then line will make the 4 distinct points. Right. Right. And let's see. So elliptic curve is the double curve of the P1, right, branched of the 4 distinct points, right? With this 4 distinct points, you can also define this J invariant. So you suppose you have 4 points. So this is 4 points. Let's say this is x1, x2, x3, x4. Right. Then you can first define the cross ratio with this number. Right, and then with this J invariant, with this cross ratio, you can define the J invariant of this elliptic curve. Double curve of this line ramified as this 4 point. Right, this is the standard things. And thus. Okay. All right, then this, you can check this is the symmetric rational function with respect to x1, x2, x3, x4. Right? It's expectable. All right? And now what I want to do is I want to express this 4 point in terms of the STU. Right? All right? To do so, like you replace just this way as t. You will see. 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 Wait. I want to reconstruct this derivation threefold from the quadratic. Okay. All right. So then you replace this z by this equation. All right. You put this. All right. Then you get this equation. All right. All right. Then this. All right. This gives us the symmetric relation between among these 4 points. Okay. So in that way, you can consider this J function. You can consider this J function as the rational function in STU, not the x1, x2, x3, x4. So you can replace this this 4 point by this STU, and then you can check this is the degree 12 over degree 12 rational function. Okay. All right, and all right. So now get back to our business. So we start for this. We start from this del Fetch 3 for the degree 1, and then we have this J function, right? And if we start from the Hessian means what? Your quartic is degenerate, and then that means your fiber is not the elliptic. I mean the degenerate things, singular things. So that means these two guys must match. So let's check. That's what you have to expect. So here, okay. Can to here. Right. So here we use just some computer, but yeah. So as we expect from here, you can find you can rewrite this rational function into this form. So some function, you find this form and this form. So again, we start from the smooth plane quartic, not from this double. I mean this del Fetch 3 for. So we don't know on this. We don't know this. So we only have this plane quartic equation, and then we can get this. All right, and then what we expect is this. So now, the thing is the next step is now we consider this del Fetch 3 for. Defined by this equation is exactly this the 28 nodal del Fetch 3 for of the degree 1. So that's what you're gonna do. All right, so this. All right, so this. All right, so here is the one small observation. So this guy is rational function, and so this guy is, roughly speaking, this guy is not defined along this curve, right? And starting from here, so this J invariant function is not defined when the intersection. I mean, this intersection point is not the 4 point, right? Meaning is this line is a tangent. Right? So like this. Right? So this equation defines the dual curve our original smooth plane quartic. So this is exactly this degree. This dual of the smooth plane quartic is the degree 12 curve with some singularities. Right? So let me denote. This is your dual curve of this smooth plane quartic. All right, and so and the rest. This is a degree 12, as I said, with some singularities. Singular points. Okay. All right, so let's look at the singularities of this dual of the C. I mean this. All right, it comes from I mean some tangent lines from the C. So you know we have you know C has some bitangent line. So this is ordinary bitangent to C, and it goes it corresponds to a node. Right? And you may have a tangent line. You consider tangent line at the ordinary inflection point. So ordinary inflection point is this tangency is the more than 2. So in quadratic case, you can have the inflection point with the tangency 3 and 4, right? So the ordinary inflection points means you have tangent 3 at the point, right? So in this case, this line makes the simple cusp. C hat, right? And you have also like you may, I mean sometimes not, but you may have the inflection point with the tangency 4. So this is it's called the hypertangent, hyperinflection. So inflection point this, and this produces the triple point. On this dual curve. Okay. All right, so it locally looks like S cubed, right, like this. Type. All right, so this inflection point, I mean the hyperinflection point, at the hyperinflection point, the tangent line, and this tangent line doesn't meet the another point, right? So this is also considered as the bitangent. So let's say the number of the ordinary bitangent, and number of let's say this, I will denote by H. This is the number of the hyperinflection point, and this is the number of ordinary inflection points. All right, then the very classical theorem, but it's very famous. The number of the bitangent. This is also bitangent, right? So this is the 28. Right, and we also know this number is the 24. Right. Okay. All right. Then. All right. So. Starting from the C, we construct this del Pezzo threefold of degree 1 with, right? All right, so we consider this equation. All right, this G4, G6 comes from the C. It has nothing to do with the del Pezzo threefold. We are just given this smooth plane quadratic. Right? And this, we have this, right? So I want to claim that this guy has exactly 28 singular points. Right, so this is the equation, and then so let's say this is the set of singular points. Okay, I will divide by this way. This is the singular points. The outside of the this is the singular points. It's outside. This equation. I mean this hyperplane. So this is the P1, 1, 1, 2, 3, and this is a V and S, T, U, V, W. Okay. All right, and this, and of course we have a singular point, the outside of the this section. So singular point. I mean the inside. Right, and we also consider this a singular point of this dual curve. Right? Right, and for this, we're not going to consider all singular points. We consider only a special type of singular point, so which is denoted by this. So this is the singular point, the singular points of the C hat. Outside this curve, G6, this G6, right? You have the sextic curve and the sextic curve, right, defined by this G6, and then this is the set of the singular point outside of this. Okay, and we also consider CV hat, a singular point. And this is a singular point at which this curve, C6, is a singular. Right? All right, then by simple computation, you can see this set and this set has the one-to-one correspondence. And this set has and this set has the one-to-one correspondence. Okay. Okay. Maybe here. Okay, and let's look at this equation again. So this guy is defined by this equation. All right, and you have this curve G6, and you have this curve G4. Right, different vertex here. All right, and we know the C check has the three types of the singularities only. So node, simple curve, and the triple point. All right. All right. So there are only three ways to. I mean, these two curves can meet each other in only three different ways. So one is the two different ways. So like one possible way is that they intersect transversally. Right? In that case, this point will be a simple cusp. Right? So you have this is smooth and smooth. They intersect the transversally. That means this is S and this is T, like something like this. So that makes the simple cusp. Right? This is first, and this second is the this. This G6 has a double point. FP. And this intersection number with this quartic FP is there too. Then it makes the triple curve, right? And different, I mean, if you meet the different rate, if these two guys meet the different rate, then they will produce the singular point which different from the other two. So this is D on U, right? All right, so that means this is what? The set of all nodes, and this is the set of all. This is the set of all the triple points. Right? Because this is a cusp and this is a triple point. Right? So that means the number of singularity of our Delphi threefold is the number of the node and the number of the triple points. Right? So here we have the number of the singular points of the V is exactly same as the number of the bitangent to our quartic, smooth quartic curve, which is 28. Right? So we get this is the number is 28, and also you can check the type of this singularity, and you can check by brute force. You can even check by brute force. This is your node, so you can check this V, and this V. This is our V. V has exactly 28 nodes. Right. So here is our main theorem. Still following. So there is a 1-to-1 correspondence between isolation classes. 28 node Pezzo 3/4 degree 1, right. And isolation classes smooth plane quartics. Right. So this is the theorem. So what I explained so far is like this. When you have this 28 node or Pezzo 3/4 of the degree 1, then you find this discriminant curve, which is the degree 12 curve in the plane, and then you take the dual, then you will get this smooth quartic plane curve. Okay? And when you have this smooth plane quartic, so you can construct in that way, you can construct this, and you can show this is the one-to-one correspondence. So this is the our main result. But let me finish this talk by one remark. There is a classical theorem which is known. I'm not sure. I couldn't find the proper literature, but they are known to be 100 years ago. But so there is a one-to-one correspondence. R solution crosses of the regular Cayley the octet and the isolation crosses smooth plane quadratic curves equipped with their even set characteristics. Right. So this is I think it is originate from the Hassett, like a 19th century. So there is a one-to-one correspondence. So we know the smooth quadratic curve has the 26 even zeta characteristic. Right? So if you drop this condition, then generically you have this map is the 36 to 1 map. Right? So, but here we have, so the Prokhorov construct is derivation 3/4 of degree 1 from the Cayley octet, more or less. Even though he starts from the 7 points, right? It's about the space locus. And we start from the smooth plane quadratic. So smooth plane quadratic, our construction don't care about the even set characteristic, but somewhere it's hidden, right? So here is the simple explanation. So here. All right, so let me explain how to get this 36 from the Prokhorov's construction. Okay, so it's like this. So you start from this 7 point, right? Right, but I choose the 4 points. On this, you choose a 7 point, right? And or determine the 6 lines, right? All right, so here, this. All right, so here our P3. We took the block at the 7 points, right? So here P1, P2, P2, P7. Right. All right. Then we have this 6 lines comes from this 4 points, right? First of all, we construct this 28 curves by plopping construction, right? And we plop this 6 curves. Then you got the new 7-point block here. Actually, this is given by, and this is the Cremona with respect to this 4 points. Okay. So this is the another contraction, and then you will have this another 7 point, like this, right? And this is the value. So see here, you choose the 4 point out of the 7, which is the 35, right? You do nothing, so then you have one more. This is a 36. So that's why you get the, this. So each even zeta characteristic gives us this Cremona transformation, sort of. So this even zeta characteristic give us this another model for the weak Fano model. So this is how involved the even zeta characteristic in this picture. Okay. I think my time is up, so let me start here. Thank you.
Questions? Yes.
So these days, for moduli of Fano variety, we have this case compactification using case compactification. This conference is about. So I guess
All of them, I think.
No, but there is a compact modular space. So you get some compactification. We're on the boundary of some changing stable. So that should correspond to some compactification for plane cortex.
Are these ones, are these before Are they before?
Yeah, it's no.
Yeah, with nodes, yeah.
We were interested mostly in rational ones, so then we didn't want to smooth them, but Valery is right.
So for the plane cortex, the simplest compactification is a projective space. Or anyway, my question is, what is that compactification for the side of plane cortex?
Well, I don't.
Or maybe you can compute this compactification now somehow easily in this case. This one-to-one correspondence.
We checked some cases when quadratic is generated, and we know, because it's algorithmic. So we know the answer on the left-hand side. Yeah, but we didn't kind of work on this. We just checked some cases to see what's going to happen with this one.
What is the K?
It's going to be more
stable limit.
It's going to be non-isolated singularities, but the nodal will look the line, the curves.
So you don't get a double.
So for point cortex, okay, the simplest compactification is the GIT question.
We don't know.
We will check. Thank you very much.
Is there a relation with the Pezzo's surface?
Yes.
Yeah. For example, the automatic group is same. And also, Yuri in his paper showed that on the class group here, on the complement point canonical divisor, there's some conventional intersection form which makes it the while group, while levels of E is the same for the Pezzo surface.
So you start from the 7 point, and then you consider this a net. Then you have the extra base point, right? To relate to this 7 point to the degree 2 case, I mean, the differential surface is degree 2, you project this 7 point from this base point. And you get the 7 point on P2. There will be a general position, linear general position. I mean, you satisfy this literature. You blow up. Then, right? And then this will be a differential surface of degree 2. And this is the double cover P2, ramified the quartic. And this is also exactly this Hessian.
But this is not a good.
So this projection is traditionally called the Gale transformation.
How about, is it related to maybe modular space of V22? Is it also described like we will see in plane quartic?
All right, so this quartic business is this 26 even zeta characteristic related to the determinant rho.
Yeah.
Determinant. But the V22, they consider this a wording problem. So you start from quartic, and then the way to way to express the this even quartic as the sum of the linear quartic. I mean the linear, yeah. Yeah, that's the way to the V22 from the quartic. So so that's why it's also related to the this even set characteristic on the quartic.
But the interesting thing is that the generated condition is different.
Yeah, that's true. Yeah, Bukai construction is not one-to-one exactly, so there is it's a variational relation. Yeah.
So you don't need any additional generated conditions. Bukai construction does, but on the other hand, Bukai construction, by some miracle, it works to start from double point. And our construction doesn't really work to start from double point.
Maybe we can force it.
Well, at least it doesn't give us 28 noodle. The Bukai construction starting from a double point is a nice smooth thing. Maybe the story is a kind of vibration related to
How about Meldon generations? If you just put your conditional point.
Then what? It's going to happen what you have already said. You get the singular on the curve sometime.
No.
I mean, you mean the singular on the
you put your point to the
on quartic, you mean?
no, quartic on T3, original T3. You start with 7 points.
Yeah. What
What is
I haven't figured out. Yeah, I'm trying. No, but yeah.
what happens with your quartic?
I think it's similar because it's projection giving construction, right? If it's not in general position, we project from the plate, but it's not in general position of the plate.
It must be no room here because we saw it. It must be single, but how about
We have a formula which
Okay.
no more questions. Well, thanks, Jehun, again. We have